Most industrial process plants require that process variables such as temperature, pressure, level, and flow be maintained at a predetermined value called set point. The effective and efficient control of a process depends on keeping a process variable as close to set point as possible. In a pneumatic control system, it's the responsibility of one instrument to ensure that the system takes corrective action to keep a process variable at set point. This instrument is called a controller. A pneumatic controller is an instrument designed to produce a corrective signal that enables a control system to maintain a process variable at set point. In effect, the controller is the control center of any control system because it determines the system's corrective action. For the most part, pneumatic controllers such as these contain the same basic mechanisms as other pneumatic instruments. They operate on the self-balancing principle. That is, they respond to changes in input by rebalancing themselves automatically. The new output from the controller reflects the change in input and causes the control system to attempt to correct the change in the process variable. In this program, we'll look at several types of pneumatic controllers. We'll see how they operate, and we'll discuss basic adjustments often found on pneumatic controllers. A part of your job will be to see that the pneumatic controllers work properly and that they're adjusted correctly. Understanding how controllers operate will help you when you're repairing a controller or tuning a pneumatic control system. Now, before we examine how each of these controllers operates, let's see what all pneumatic controllers have in common. Pneumatic controllers perform four basic functions. They measure, compare, compute, and correct. First, the controller measures the value of the process variable. It can do this directly by using a primary sensing element, or it can receive a signal from another instrument, such as a transmitter. The controller then compares the measured signal to set point for the process. As we'll see later, set point can be developed in several ways, depending on how the controller is built. The thing to remember is that in the controller, the measured signal is compared to set point. If the process variable is at set point, the controller will be in balance, and there will be no change in its output. However, if there's a difference between the measured signal and set point, the controller detects this and computes the difference. Usually, deviations from set point will cause the controller to be out of balance. Then the controller produces a corrective output signal that causes it to rebalance itself. The output signal is also sent to the system's final control element, which is manipulated in some way in an attempt to return the process variable to set point. The corrective response that a controller provides can take many forms. As you probably know, pneumatic control systems control process variables in different ways. The output response that a controller provides because of a process disturbance is called its control action, or control mode. Most pneumatic controllers can be divided into groups based on the output response they produce when a process variable deviates from set point. In this program, we'll study four types of controllers: proportional or P-only controllers, proportional plus reset, or simply reset controllers, proportional plus rate, or rate controllers, and a combination of all three, proportional plus reset plus rate controllers. Each of these control modes causes a controller to produce an output that makes it respond differently to changes in a process variable. To understand these differences, we'll look at a series of graphs representing how controllers react to changes in process variables. We'll concentrate on how actual controllers are designed to provide these control modes later in this program. The graph we'll use has two scales. The orange scale represents the input signal to the controller. Since the signal comes from a process transmitter, it directly represents the present condition of the process. It's marked off in PSI from 3 to 15. The yellow scale represents the controller's output. It's also marked off from 3 to 15 PSI. A dashed line represents set point for the system. Well, let's see how a proportional or P-only controller would respond to a disturbance that causes the process variable to move away from set point. These two curves illustrate the changing values of the controller's input and output as it tries to return the process variable to set point. The orange curve represents the input to the controller, and the yellow curve is the output produced by the controller. Normally, these two curves would be produced at just about the same time, but we've separated them to make them easier to compare. This distance represents the time it takes the controller to return the process variable to set point. With proportional control, any changes in the process variable result in proportional changes in the controller's output. There's a continuous linear relationship between input and output. The process variable is at set point for this portion of the graph, so both input and output are at set point. Here, the process variable started to move away from set point due to a disturbance. The controller measured the change in the process variable and responded by producing a proportional output, moving the process variable back towards set point. The controller then measured the decrease in the value of the process variable and decreased its output proportionally. Eventually, proportional control caused the process variable to settle out. But it didn't return to set point. The process variable settled at a new value, called a control point. This difference between the control point and set point is called offset. Offset refers only to the process variable when it settles out at a point other than set point. Offset results from the fact that proportional controllers respond only to changes in input. If the controller's input isn't changing, even if the process variable didn't get back to set point, the controller's output will not change. In some processes, a certain amount of offset is acceptable, but other processes require additional control. One control mode that is often added to P-only control is reset control. The controller is referred to as a proportional plus reset, or simply a reset controller. Reset controllers repeat the amount of proportional output for the period of time that the process variable is away from set point. A reset controller provides an increasing amount of output so that it can return the process variable to set point. Here's what the input and output curves look like for a typical reset controller. Again, a disturbance caused the process variable to deviate from set point. The controller responded by producing a corrective output. With reset, the controller continuously repeats its proportional output for as long as the process variable is away from set point, based on the amount of deviation. The increased output from the controller effectively gets rid of offset. The controller's output levels off at a higher value than set point. This does not represent offset. It's just the extra amount of output necessary to maintain the process variable at set point. Now, in some processes, it's critical to get the process variable back to set point as quickly as possible. Here, even though reset control eliminated offset, it took a long time to do so. In some processes, it's important to quickly stop any changes in the process variable. To do this, another control mode can be added to P-only control. It's called proportional plus rate, or rate control. With rate control, the controller measures the speed at which the process variable moves away from set point and rapidly boosts its output to stop the change. A rate controller advances the amount of output based on the expected rate of deviation in a given period of time. As you can see, the process variable settled out quicker than it did with reset control. But as with P-only control, there is offset. It would seem then that the most ideal controller would combine the best features of rate, reset, and P-only control. We can call the controller represented here a proportional plus reset plus rate controller. Since it combines all three control modes, it's typically called a three-mode controller. As the process variable moved away from set point, the controller's output received an immediate boost due to rate control. Then reset control eliminated offset and returned the process variable to set point. Each of the control modes we've just examined has its good points and its limitations. For example, even though a three-mode controller may seem to be the best one, it's too sensitive to be used in some processes. You're likely to work on pneumatic controllers that provide one or all of the control actions we've just discussed. What makes these controllers different is the way their internal mechanisms are arranged to provide these control modes. In upcoming parts of this program, we'll look at the actual controllers just like these, and we'll see how they're designed so that they provide different control modes. We'll examine a typical P-only controller in a moment. At this time, read over the text material and make sure you have a good understanding of controllers before we go on. Pneumatic controllers have three basic mechanisms, just like all self-balancing instruments. Now, these mechanisms are an input, an error detector, and an output balancing mechanism. An input mechanism converts a change in a process variable into a mechanical motion, which is sensed or detected by the error detector. The output from the error detector, called back pressure, is used by the output balancing mechanism to develop the controller's output signal. In this program, we'll identify how these basic mechanisms are utilized so that the controller measures the input signal, compares it to set point, computes the difference, and generates a corrective output signal. Now, in a proportional controller, the basic mechanisms work together to enable the controller to produce an output that is proportional to its input. We'll examine how this controller provides P-only control in a few minutes. Now, first, let's see how the controller's basic mechanisms can be arranged so that it can provide P-only control. In this illustration, the input mechanism is a bellows, which we'll refer to as an input bellows. The input signal from a transmitter is applied to this bellows. This is where the controller measures the value of the process variable. We'll use a pressure gauge to indicate the value of the input to the controller. The input bellows exerts a force on one end of a beam. The beam is pivoted at its center. As you remember, the second function of a controller is to compare the measured signal to set point. Set point for this controller is established by the tension of a spring, which opposes the force of the input bellows. When the process variable is at set point, the two forces are balanced and the beam is stationary. If the process variable exceeds set point, the controller's input increases, expanding the input bellows. This increases the force of the input bellows and overcomes the spring tension. The beam moves up, causing the controller to be out of balance. The error detector mechanism is a flapper nozzle arrangement. Changes in the position of the flapper relative to the nozzle result in changes in back pressure, which builds in a compartment behind the nozzle. Normally, there would also be an air supply and a fixed restriction behind the nozzle, but we've omitted them for the purpose of simplifying the illustration. This is where the controller computes any difference in the measured signal and set point. If the beam's position changes, It changes the relationship between the flapper and the nozzle, which results in changes in back pressure. The back pressure compartment is connected to a pneumatic relay, shown by a block labeled R. Its purpose is to convert changes in back pressure to proportional changes in the controller's output. We'll use another gauge to indicate the value of the output. The output signal is used for two purposes. For one, it's fed to the output balancing mechanism, another bellows, which we'll call a feedback bellows. If input changes, the new output causes the feedback bellows to bring the controller back into balance. The output signal is also sent to position a final control element. This is the corrective function of the controller. Right now, the controller is in balance, with its output proportional to its input. Let's see how all of the controller's mechanisms work together when the process variable exceeds set point. The input bellows expands, and its force overcomes the tension of the set point spring. The controller is now out of balance. When the input bellows expanded, the beam pivoted, bringing the flapper closer to the nozzle and increasing back pressure. The relay converts the change in back pressure to an output that reflects the increase. The increase in output is supplied to the feedback bellows, which expands and brings the controller to a balanced condition that reflects the difference between input and set point. The controller's new output is proportional to its new input. So the controller has responded to an increase in the value of the process variable above set point by producing an output that is proportional to the increase. In this way, the controller is providing P-only control. A proportional controller's output changes only if its input changes. This is characteristic of all proportional controllers. We've just seen one simplified example of how a controller can be designed for proportional control. Other controllers may have different mechanisms and may balance themselves in different ways, but the result is always the same. The controller responds to changes in a process variable by supplying a proportional output. Now, it's your responsibility to see that pneumatic controllers are properly adjusted. To do this job correctly, you need to understand basic control modes and how controller adjustments affect these modes. There are two basic controller adjustments: set point and proportional band or gain. Let's look at these adjustments as they relate to the simplified controller illustration we just looked at. When set point is adjusted, it establishes the point or input value around which the controller will provide its controlling action. Set point is adjusted on this controller by varying the tension on this spring. As you remember, the spring exerts a force in opposition to the force from the input bellows. To adjust set point, spring tension is increased or decreased until the controller's output signal causes the control system to stabilize at its desired set point value. At this point, we've established the value of the process variable around which the controller will provide corrective action. The next adjustment, called proportional band, determines how much output the controller will provide for a given input. Proportional band is the ratio of a controller's input to its output. There's a difference between proportional band and gain, which you'll read about in your text. For the purposes of this discussion, we'll talk about controllers that have a proportional band adjustment. Proportional band is the change in input required to produce a full range change in a controller's output. It's usually expressed as a percentage, input divided by output times 100. In this controller illustration, proportional band is adjusted by moving the pivot. If the pivot is moved this way, it only takes a small amount of input motion to cause the beam to move the flapper close to the nozzle. As a result, the controller will produce its full range output. This corresponds to a narrow proportional band setting, where a small amount of input change produces a greater amount of output change. Moving the pivot in the opposite direction produces the opposite effect. A larger amount of input change is needed to produce a full range change in output. So this would correspond to a wide proportional band setting. The illustration that we just saw is a simplified version of what a P-only controller looks like inside. We can use it to compare how an actual P-only controller operates. This proportional controller is designed to control temperature in a process. Its input mechanism is a Bourdon tube, which is connected to a temperature bulb. The Bourdon tube either curls or uncurls as process temperature changes. This is the process measurement for the controller. Most of the controller's internal mechanisms are hidden behind this cover. We'll use an illustration and exaggerate movements to explain how this controller operates. The Bourdon tube is attached to a movable plate. Set point is established by rotating the plate with this knob. This positions the Bourdon tube so that the process stabilizes at its desired set point temperature. The tip of the Bourdon tube is attached to one end of a lever whose pivot is here. If temperature increases, the Bourdon tube uncurls and the tip of the tube raises one end of the lever. This means the measured signal has exceeded set point. As the lever pivoted, it moved closer to a nozzle. The lever acts like a flapper. The end of the lever and the nozzle make up the controller's error detector mechanism, which computes the difference between the measured signal and set point. Since the lever is now closer to the nozzle, back pressure increases and is converted by a relay to an output signal, which is sent to the system's final control element as a corrective signal. The output signal is also supplied to a bellows, which is the controller's output balancing mechanism. The movement of the bellows is limited by this spring, which is part of a lever and block assembly. The block is the proportional band adjustment. As the increased controller output is supplied to the bellows, it expands, raising the pivot up and moving the lever away from the nozzle until the controller is again in a balanced condition. So the controller has responded to an increase in process temperature by producing a proportional corrective output signal. For the past few minutes, we've examined a typical P-only controller. Its basic mechanisms are arranged so that changes in a process variable away from set point are converted to a proportional change in output. As we mentioned earlier, P-only control can lead to offset, which is undesirable in some processes. To eliminate offset, some controllers add reset control to P-only control. We'll see how a controller can provide reset control when we return. Right now, take the time to read the text material on P-only controllers and have your instructor clear up any questions you may have before we continue. A proportional plus reset, or reset controller, combines proportional control with reset control. The reset portion of the controller's output repeats the amount of proportional output for as long as the process variable deviates from set point. The addition of reset eliminates offset because the controller is designed to supply an increasing amount of output to counteract the deviation of the process variable. This increasing amount of controller output is based on repeating the controller's normal amount of proportional output. To better understand how a reset controller can do this, let's modify the controller illustration we used in the last segment. We've added another bellows directly across the beam from the feedback bellows. We'll call it a reset bellows. The reset bellows exerts a force that opposes the force of the feedback bellows. The output from the controller is now supplied to two components, the feedback bellows and the reset bellows. But the two bellows don't pressurize at the same time. There's a variable restriction in the line to the reset bellows. Its purpose is to regulate the amount of reset action the controller provides by delaying changes in output from reaching the reset bellows. This has the effect of altering the normal balancing of the controller when the process variable deviates from set point. It also causes the controller's output to be greater than it would be with P-only control. Let's see how. If the process variable increases, the input bellows expands and causes the beam to pivot as before. Since the flapper is closer to the nozzle, back pressure increases. So, output increases. The increase in the controller's output is supplied to the feedback bellows and the reset bellows. The feedback bellows begins to expand in an attempt to rebalance the controller. But the expansion of the reset bellows is delayed due to the variable restriction. As the output bleeds into the reset bellows, it provides an opposing force that counters the normal balancing action of the feedback bellows. This force tends to keep the flapper closer to the nozzle than if the feedback bellows were unopposed, as was the case with the P-only controller. As a result, the controller's output is greater than it was with the P-only control. As long as the input signal is above set point and the controller's output is increased, output will continue to bleed into the reset bellows, and it will continue to expand. The controller is now even more out of balance. The flapper continues to move closer to the nozzle, resulting in further increases in the controller's output. When the process variable starts to return to set point, the input signal to the controller decreases. The input bellows contracts, and the set point spring forces the beam downward. When the process variable is at its set point value, the force of the input bellows will once again be balanced by the force of the set point spring. In addition, the forces of the feedback bellows and the reset bellows will balance. The controller's output is now used to position the system's final control element so that the process variable stays at set point. So the addition of a second bellows, along with a variable restriction, delayed the normal balancing action of the controller. This enabled the reset controller to produce an increasing amount of output for the time that the process variable was away from set point. As a result, the controller was able to eliminate offset. Now, besides having a set point and a proportional band or gain adjustment, reset controllers have an additional adjustment called a reset adjustment. The reset adjustment for the controller in this illustration is the variable restriction. It regulates how much output bleeds into the reset bellows. This determines the amount of reset action that the controller will provide. Opening up the restriction increases the amount of pressure that is allowed to bleed into the reset bellows. In this case, the controller would provide more reset action because the force of the reset bellows would tend to hold the flapper closer to the nozzle. On the other hand, if the restriction were closed, the controller would provide less reset action. This is true because the feedback bellows would be able to expand more, just like in the P-only controller illustration, and cause a decrease in output. Again, we can compare the illustration of the controller we've just seen with an actual reset controller. A Borden tube is the controller's input mechanism, which measures the signal from the process variable. The tip of the tube is connected to a beam. The other end of the beam and a nozzle make up the error detector mechanism, where the measured signal is compared to set point. For this controller, set point is developed a little differently from the ways we've seen so far. Instead of using a spring to establish the proper distance between the flapper and nozzle, this controller's set point is adjusted by actually moving the nozzle in relation to the beam. Here's the feedback bellows above the beam and the reset bellows underneath it. with the variable restriction in the line to the reset bellows. We'll use an illustration and exaggerate movements to show how this controller operates. Let's watch as the controller provides reset action in response to an increase in input. The bourdon tube uncurls, meaning the measured signal has exceeded set point. As a result, the beam moved closer to the nozzle. Back pressure increases and is converted by a relay to a corrective output signal. The controller's output signal is sent to the two bellows. The feedback bellows expands, but the variable restriction delays the expansion of the reset bellows. As pressure builds up in the reset bellows, the force that it exerts opposes the force of the feedback bellows, which has the effect of holding the beam closer to the nozzle. The output from the controller will continue to increase as long as the process variable is away from set point. This enables the controller to return the process variable to set point to eliminate offset. Now that we've seen how this reset controller operates, let's look at its adjustments. Its set point adjustment is labeled percent setting. The percent setting dial is specific to this controller, but it has the same purpose as the set point adjustments we've seen so far in this program. By adjusting it, the controller's output is set at a value that causes the control system to stabilize at its desired set point value. The proportional band adjustment is this dial, marked off from 0 to 10 in a counterclockwise direction. The 8 setting that you see here corresponds to an 80% proportional band setting. This is the reset adjustment for the controller. It's adjusted to vary the output bleeding into the reset bellows. The units of measurement used on this controller are minutes per repeat, or the number of minutes it takes the controller to repeat its proportional output. So the 0.5 reading means that the controller will repeat its proportional output every half a minute. For some reset controllers, the units of measurement for the reset adjustment are repeats per minute, the inverse of minutes per repeat. However, the purpose of the reset adjustment is the same, to determine how much reset action the controller will provide when the process variable deviates from set point. For the last few minutes, we've looked at a typical reset controller. The controller repeats its proportional response as long as the process variable is away from set point. The increasing output from the controller returns the process variable to set point and eliminates offset. Go over the material in your text at this time and make sure you understand the difference between reset controllers and P-only controllers. When we come back, we'll see how a controller can provide proportional plus rate control. In some processes, it's important for the control system to quickly stop any deviations in a process variable from set point. Now, one type of controller that can do this is a proportional plus rate, or rate controller.